Feasible regions have a lot of practicality in the real world. For mathematical purposes, my big emphasis is teaching you how to use y and x in a function. And so what happens is normally x is your input, y is your output, but in a problem with a feasible region, typically your x and y and other variables are a bunch of inputs put together. So now x and y are both inputs. Now the question is really asking you, the feasible region has vertices. So it's kind of like a square, a rhombus, a rectangle, a parallelogram, a polygon. And you're trying to find the minimum, maximum, or sometimes they want you to find the middle value. In this problem, we're looking for the minimum. So all we have to do is take each x and y and plug it into this equation. And whichever gives us the smallest value is going to be our answer to this feasible region. So you take f of 3 and 1, and what happens is you get negative 2 times 3, and then that's minus 4 times 1, which is going to be negative 6 minus 4, which is the same thing as negative 10. Alright, looking good. Each problem does the same thing. Negative 2 times 5 minus 4 times negative 4, negative 10, negative 4 times negative 4 is positive 16, which gives us a positive 6. So far this isn't the minimum value, so we're not going to be using this as an answer. 0, 0. A lot of students will make assumptions. They'll say, oh, 0, 0 has to be the smallest. Well, it's based on the equation that's generated by your feasible region. So don't jump to any conclusions. 0 minus 0 is just 0. Again, negative 10 is smaller than 0, so that shouldn't be our answer either. Last but not least, negative 1, negative 3, negative 2 times negative 1, minus 4 times negative 3. We've got negative 2 times 1, which is positive 2, plus positive 12, which is 14. That's the biggest one of all, so this would be our maximum value, but not very useful. So there's our answer. This is the minimum value for the feasible region.